be factored by grouping. We could do this without factoring by grouping if we graphed it, look for x-intercepts, maybe use a little synthetic division factor theorem and do it that way. But I believe we can do this. Actually, sine graph will probably fit on there as well. S of t equals t squared times t minus 5 minus 8 times t minus 5. I noticed that factoring by grouping seems to work because when you multiply these two together, you get 40t cubed, and when you multiply these two together, you also get 40t cubed. 40t cubed right there. 40t cubed right there. When those products are the same for a 4-term polynomial, it will always be factorable by this process of factoring by grouping. So I group the first two terms together and factor out a t squared, group the last two terms together and factor out a negative 8. And then what makes it work is that the t minus 5 is a common factor of those two components of the expression. So it's going to be t squared minus 8 times t minus 5. These are the factors. Once we have these factors, the zeros are easy to come by, since they're no more complicated than quadratic factors. T squared minus 8 equals 0, or t minus 5 equals 0. So t could be 5, or t could be one of the 2 square roots of 8. Plus or minus the square root of 8. If you like simplified radicals, it's going to be 2 times the square root of 2. Otherwise, 2.8 something, I believe. Plus or minus 2.83, probably, something like that. Sine graph for s of t. No derivatives yet, just the function itself. So the sine graph of s of t is just telling us where it's above the x-axis and where it's below the x-axis. If we wanted to graph the function itself, or if we just want to know where it's positive, where it's negative, that's what it's doing. So the sine graph for s of t would include all of its zeros. So 5. 2 times the square root of 2, and negative 2 times the square root of 2. We would just need to evaluate s at negative 3, I guess. I don't know if that seems too close to negative 2 times the square root of 2. To tell the difference, we could go negative 4, but negative 3, 0, positive 3, and 6. And although if I'm going to pull out the calculator, it would be easy enough to just graph it and put pluses where the graph was above the x-axis and minuses where the graph is below the x-axis. Nonetheless, I'm going to show how the procedure can be done and only require the calculator to help me evaluate the function. So x to the 3rd power minus 5x to the 2nd power minus 8x plus 40. Quick look at the table to make sure that the table setup is set to independent variable ask. Second window. Press second window that looks at the table setup, and the independent variable is in fact set to ask. So second graph or second table will take us to the table menu. And so we can evaluate the function at negative 3. We see that it is negative there. And at 0, we see that it is positive, positive 40. And at 3, it is negative. And at 6, it's positive. Positive 28. So the function s does not have any zeros with even multiplicity. All three zeros have odd multiplicity, so we do get a minus plus minus plus, swapping back and forth in the sign graph. We don't have it failing to change signs on either side of the zero. Way too many windows open. Let's see what we can do here. Back there, close it, leave it, close it, there. Now we turn our attention to the first derivative. We want to find s prime and all first order critical numbers. Same function, of course. So the function s, what is this? Didn't think it would overwrite it like that. Put it over there. So s prime of t equals 3t squared minus 10t minus 8. We can use the quadratic formula if necessary, but can we factor this? Maybe a 3t and a t, and I'm thinking negative 24 and negative 10, product of negative 24, sum of 10, so I'm thinking 12 and 2, maybe negative 12 and positive 2. We could get a negative 12 by multiplying 3t by negative 4, and we could get a positive 2 by multiplying 2 by, well, we can just write it down. 2 times 1 is 2. So I think this does it. We get negative 12t plus 2t is negative 10t. We get negative 8 on the end. We get 3t squared in front. So this seems like an okay kind of factored form. So if we look for the zeros, the zero of this first factor is negative 2/3, and the zero of this other factor is positive 4. So sign graph for s prime of t. We're going to have negative 2/3 there and 4 there. And of course we can still use these test numbers. But if you think about this graph just for a little bit, it's a parabola. The graph of the first derivative is a parabola. It opens up. So if I were to superimpose that on this picture, it would look something like that. Where the graph is above the x-axis, there are going to be pluses. Where the graph is below the x-axis, there are going to be minuses. So s prime of negative 1 is going to be positive. S prime of 0 is going to be, well, negative 8. S prime of 5 is going to be positive. So you can check the specific values. But based on what we know about quadratic functions, because we just beat quadratic functions to death in college algebra, so we know what's going on with quadratic functions. The next one will be linear, and it'll be even easier. So what do the pluses tell us about the original function s of t? So this is s prime of t. S prime of t is positive, s prime of t is negative, s prime of t is positive. S of t is increasing. S of t is decreasing. And s of t is increasing. I know it feels like we've done this before because, well, we've done this before. That's why it feels that way. Any relative extrema?
Well, you got a relative max at negative 2/3.
Yep. Relative max, because it goes from increasing to decreasing. And it's continuous there at x equals negative 2/3, and
Relative min at 4.
there we go. It goes from decreasing to increasing. Relative min, bottom of the valley, at x equals 4. And then E. Find S double prime of t and all second order critical numbers. Indicate the intervals where S of t is concave up, where it's concave down, and find any inflection points. Basically, we're just putting together the things that we've done in previous sections. So look up here and just reminder of the function S of t. There's S of t. S prime of t, we said, was 3t squared minus 10t minus 8. S double prime of t equals 6t minus 10. So there's the second derivative, and we have one second order critical number. What is the one second order critical number? 10 over 6, or 5 over 3. No, something like that. There it is. So 5/3. What we know about linear functions, 6t minus 10. 6t minus 10 is a straight line. Does it slant up to the right or down to the right? 6t minus 10 is positive slope, so it slants up to the right. So if we were to superimpose the graph of the second derivative on this sine graph, it would look like that. There would be pluses where the graph is above the x-axis, and minuses where the graph is below the x-axis. If you want to use the critical numbers, you can use 0 and 2, I guess. 6 times 0 is 0, minus 10 is negative 10, so S double prime of 0 equals negative 10, the minuses. And S double prime of 2, 12 minus 10 is 2. That's positive, so we get the pluses. Now, the minus and the pluses tell us what about the original function S? S of t is concave down with the minuses and concave up with the pluses. So tell me, this is all review, right? Every single bit of this we've done before. Except maybe the zeros. I guess the zeros of the original function we did in algebra someplace. We haven't dwelt that much on that in calculus. Okay. I want to relate this to the idea of rectilinear motion. A particle moving back and forth along a straight line. I want to see what the graph tells us. If S of t is the position function, the rate at which the particle is changing, or the rate at which the position is changing with respect to time, is going to be the velocity function. And the rate at which the velocity is changing with respect to time is going to be the acceleration function. The derivative of the velocity function is going to be the acceleration function. So what we want to be able to do is tell where, on what intervals, the function is on the positive side of the origin, on what intervals it's on the negative side of the origin, on what intervals the velocity is positive, basically it's moving in the positive direction, and what intervals it's moving in the negative direction, and then on what intervals it's, well, ultimately we need to know something about the sign of the acceleration, but we put that together with the sign of the velocity and it'll tell us whether the particle is speeding up or slowing down. Speeding up or slowing down. So let's see. So I'm supposed to make up a graph here. Sounds like a job for a good GeoGebra demonstration. Unfortunately, don't quite have one. Let's see. Let's start right here. Particles on the positive side of the origin, and let 1 second tick away. And 1 second ticks away, and the particle goes up here. There's a horizontal tangent line. Another second ticks away, and the particle kind of does that. don't know if I want to necessarily a horizontal tangent line, but let's say something like that. And another second ticks away, and let's just decrease for a while. Does this, and then another second ticks away, and it does this the rest of the way. This will probably give us enough to talk about. What we want to try to see is try to identify some key points here. Hopefully that's a key point there. That's a key point there, and maybe that's a key point, and maybe that's enough of them. Okay. What this is the position of the particle as time passes. Now the particle is just traveling back and forth along a straight line. You can envision that line as going to the right and to the left if you want to, and let the right be positive and the left be negative. Or you can let it be moving up and down, and let the up be positive and the down be negative. Or you can make the thing going up at an angle. That would be confusing, though, I would think. So I'm going to imagine the particles moving vertically, so it'll correspond with the y coordinate. So the particle starts, let's say, right here. And when 1 second ticks by, the particle goes up this far. And there it is. This is t equals 0, and this is t equals 1. 1 second. And this is where the particle is after 1 second. Now, another second goes by, and what does the particle do? It goes back right there. And that's where it is at t equals 2. T equals 2 between the second and the third second. T equals 3. What does it do?
It goes upward.
It goes, well, from 2 to 3.
2 to 3.
2 to 3, yeah.
Yeah.
2 to 3, it continues downward to about right there. So t equals 3 right there. And then another second ticks away. During that second, where does it go? Up just a little bit, from there to about there. That's where it is at t equals 4. And then at t equals 4, it takes off, right? T equals 4 the rest of the way. Looking for a color, bright blue is good. The rest of the way, it does something like that. And then it's working its way straight up, and I don't know where it is at t equals 5, slightly above that, it looks like. So the particle's doing this, and this, and this. What we want to know is when the particle is on the positive side of the origin. Now the origin is basically the x-axis. The origin is y equals 0. If the particle is above the x-axis, it's on the positive side of the origin. If it's below the x-axis, it's on the negative side of the origin. So if we're just breaking this down as far as these intervals go, from here to there, the particle is on the positive side of the origin. And from there, basically the rest of the way, the particle is on the positive side of the origin. And the other interval in between, it's on the negative side of the origin. Another question we might ask is, when is the particle moving in the positive direction? Now, up is the positive direction, down is the negative direction. So during what intervals is the particle moving in the positive direction? Now, let's go red maybe. 0. Maybe to there. At 1, it is stationary there for an instant and changes direction and then heads down in the negative direction. And it goes in the negative direction until when? 3. At 3, it turns and then it goes in the positive direction from that point on. So from there all the way to there, it's headed in the positive direction. So orange is where it's, orange is what? It's where on the positive side of the origin. Red is where it's headed in the positive direction. Now, it's on the positive side of the origin when S of t is positive. It's headed in the positive direction when S prime of t is positive. When it's increasing. When it's increasing, when it goes up at first, or when it's at 3 and it goes up the rest of the way. That's where it's increasing. We could talk about where it's concave up or where it's concave down. This basically the sign of the acceleration, the S double prime of t, but we don't want to talk about that. It's going to be more significant to put that together with the sign of the first derivative and answer this question. When is the particle speeding up and when is the particle slowing down? So we need to talk about speed. We need to talk about speed. The velocity of the particle, S prime of t, is v of t. So this is where v of t is positive. The speed is the absolute value of the velocity. We know velocity is a signed quantity. It's a vector quantity, but if it's just one dimensional, it's positive and negative, and of course it has absolute value. The speed is the absolute value of the velocity. So speed equals the absolute value of v of t when is the particle's speed increasing? Looking at the graph, I guess we need to think about when is the absolute value of the slope of the tangent line increasing? And when is the absolute value of the slope of the tangent line decreasing? What's going on from between 0 and 1? Let's consider this.
It's decelerating.
We've got slope of the tangent line there. And a little bit of time passes, and we have the slope of the tangent line there. And then we have the slope of the tangent line there. Let's think about what's happening to the not so much the slope of the tangent line, but the absolute value. So we just have to answer this. What kinds of lines have slope with greater absolute value? Steep lines or not so steep lines? Okay. Steep lines. Take a steep line, the slope might be 10, might be negative 10, but it has a greater absolute value than one that's close to horizontal. One that's close to horizontal, its absolute value of its slope is close to 0. So we're going from a line that's kind of steep to a line that's not so steep to a line that's basically horizontal. So what's happening to the absolute value of the slope of the tangent line as we go from 0 to 1? It's decreasing, so it's slowing down. The particle's slowing down. The velocity is going from positive numbers to smaller positive numbers to 0. But more importantly, the particle is slowing down. Now, when it gets there, let's see. The slope of the tangent line goes negative, but it has greater absolute value than 0. And then greater absolute value for a little bit. And then right here, remember we talked about inflection points in that, what was it, spread of a virus or whatever it was, the very last example we did at the end of class. And we came to an inflection point, and that was kind of an optimal value of the first derivative, and then it got suddenly less steep than that. So from 1 to 2, I want to say it's speeding up. Because the slope of the tangent line is going from 0 to the absolute value that is increasing. Then, let's see, from there, it looks like it's headed back towards 0, so slowing down. And then speeding up, getting steeper, getting steeper, getting steeper, so speeding up. How do we know? How do we tell when it's slowing down and when it's speeding up? Well, we can tell by something the shape of the curve. Look at the basic shapes that we've got here. We've got this shape. We've got this shape. We've got this shape. And then we've got this shape. I think these are the four shapes that I need here. So let me summarize this. This, and then this. Can you look at that and tell me the sign of the first derivative and the sign of the second derivative? Basically, I'm going to set up a chart here. Sign of v prime, not v prime, s prime, it's actually the velocity, and the sign of s double prime of t. Here, is the function increasing or decreasing? If it does that, increasing or decreasing? It's increasing, so first derivative is positive. Is it concave up or concave down?
Down.
Down.
Convex up.
So the second derivative is negative. Sine of s prime. This next one. So there's 1, 2, 3, 4. The second one. Is it increasing or decreasing? Decreasing. So s prime is negative. Concave up or concave down?
Down.
Down. Next one, is it decreasing or increasing? Decreasing. So s prime is negative. Concave up or concave down? Up. Last one, increasing or decreasing?
Increasing.
Concave up or concave down? Up. All right. So in each one, I want to answer the question, is it speeding up or slowing down? Steep. I want to go with a different color. Let's go with red. That's what I was going for. Come on, red. Steep. Not so steep. Not steep at all. Speeding up or slowing down? Slowing down. Okay. Not steep at all. A little steeper. A lot steeper.
Speeding up.
Speeding up. All right. Kind of steep. Not as steep. Not very steep.
Slowing down.
Slowing down. And one more. Not very steep. Steeper. Really steep. Speeding up. If you know the sign of the first derivative and the sign of the second derivative, what do those signs tell you about whether it's speeding up or slowing down? How can you tell?
They're matching at speed.
Matching?
When they're opposite, they're slowing down.
When they're opposite, they're slowing down.
Did you copy the graph and then just like post it right beside the chart just for a second? No, I did.
I'm not sure.
Just go up.
You really want a copy of that?
No, it's alright.
I could. I could if that would help. That much of it, maybe?
That's fine.
Whoops. Just want to go down here and make it really small. Ah. No!
There it goes.
No!
Erase, but use your eraser.
Woo! All right. Yeah. For what it's worth, there you are. So it's slowing down, and then it's speeding up, and then it's slowing down, and then it's speeding up. That's what's going on. So we're going to break this down, and we'll look at the zeros of the function. We'll look at the critical numbers. We'll look at the second order critical numbers. And that'll subdivide this thing into, I don't know, maybe half dozen or more different intervals. On each interval, we want to know positive side or negative side of the origin, positive direction or negative direction, positive direction, negative direction, and then speeding up or slowing down on each interval. And I'm hoping that this first one, so basically I've gone through all that. And that too. So, and pretty much this as well. So the graph, what can I do with this? If I just look at the top part of it, the first four, if we disregard the location, and the graph looks like, well, basically this, and what was the other one? That. Then we can fill in the direction. The location is simply whether the graph is above the x-axis or below the x-axis. So I'm not going to worry with that. But the direction sine of v of t, it is positive. Sine of a of t, that is negative. It was a minus. It was a minus plus and a plus. And so we filled it in like that. So slowing, speeding, slowing, speeding. There we go. Same thing that we just had. Got a little table to go with it. This function is different from the previous one. Perhaps it would have been good to use the previous one to do this type of analysis. But let's look at it. It looks like a lot of the work has been done for us. So we'll accept the fact that we did that previous work, and then we'll just rely on some of the work that's been done for this one. If you want to go back and start this one from scratch, that'd be okay. But let's look and see what's been done to this point. So we got another third degree polynomial function. S of t equals t cubed minus 11t squared plus 24t plus 28. Analyze the motion for the particle just for t greater than or equal to 0. We included negative values of t in the one that we did, but this is just t greater than or equal to 0. So we take the derivative. Actually, no. We factor the expression, and I get t minus 7 times t squared minus 4t minus 4. Sadly, the t squared minus 4t minus 4 does not factor, but it has nice enough zeros, I guess. 2 plus 2 times the square root of 2. And the other one perhaps was 2 minus 2 times the square root of 2. But 2 minus 2 times the square root of 2 is negative. So I'm not going to consider that one. We're just going to consider what happens greater than or equal to 0. We're thinking of t as the passage of time, and we're going to start at a point and look to the future. So just the positive ones. So if I have I have a graph here. So if I go ahead and put the zeros, well, 7 is right there, and 2 plus 2 times the square root of 2, the 4.8, is right there. So those are the zeros, and if you would like me to be consistent with the colors that I'm using, I think in the previous one I used orange for the original function. So there we go. There are the zeros. Take the derivative. That's easy enough. It's a polynomial. You can check me on it, but it looks like 3t squared minus 22t plus 24. And that does factor. So if we were to set that equal to 0 and solve for t, we get a couple of zeros. T equals 4/3 and t equals 6. So I'll put those in red. 4/3. What's happening at 4/3 on the graph? Looks like a relative maximum there. And 6. There's 6 right there. So relative maximum and a relative minimum. That happens at 6, apparently, from the graph. Now, one more derivative, a of t. A of t, we take the derivative and we get 6t minus 22. So 6t minus 22. 11/3 is the second order critical number. And 11/3, let's go with, what, this pink? Oh no, bright blue, I guess is fine. 11/3 is 3 2/3. 3 2/3. What's happening to the graph at 3 2/3?
Inflection point?
There is an inflection point right there. It goes from concave down to concave up. Concavity changes at a point where it is continuous, so that point is an inflection point. Analyze the motion. The location, direction, or acceleration of the particle can change at each of these zeros. So the intervals to be considered are those formed by zeros of these three functions. So we've got, and let's see if I can scroll down a bit. We've got these intervals. I wonder if it might be better to do this. Let me take this and put it on the next page. And then we'll, that's not too big, come back, and that will take the graph. I think it would be helpful to have the graph, if not superimposed on it, but to have the graph as a handy reference.
So would we be expected to come up with that table? Right?
Basically, yes. Basically, you want to come up with a table. If I give you kind of the substance of the table, the more of the table I give you, the easier it is for me to grade, but I have to resist the temptation for easy grading and have you produce as much of this as possible. But you see where the intervals come from. You have all these zeros, the 4/3, the 11/3, this evidently, this orange one, was 2 plus 2 times the square root of 2, and then the red 6, and then the orange 7, and then on out to infinity.
It was basically given to us anyway, though, right? Up there.
Right. If you successfully find the zeros of the original function, the zeros of the first derivative, and the zeros of the second derivative, and put them in order from left to right, those are the intervals that you need there. So I think we can use the graph, since we have access to the graph, for most of this. Based on what we know about the graph, we could do sine graphs and so on. But I think we can pretty much use the graph to tell the location, the direction, the sign of the first derivative, and then see if it's speeding up or slowing down on each of these intervals. So from 0 to 4/3, the location, the graph, is above the x-axis. So it's on the positive side of the origin. So I'm just going to signify that with a plus. And in fact, it might be a little bit more efficient. Pedagogically, maybe it would be smart to go across each row. But if we just look and maybe look at the sign of S of t, maybe it'll be more efficient because we can say, okay, at 4/3, it's between 4/3 and 11/3, it's still above the x-axis. Still above the x-axis. And from 11/3 to 2 plus this 2 times the square root of 2, still above the x-axis. And it's not below the x-axis until we get to 2 plus 2 times the square root of 2. From there, it's below the x-axis. And between 6 and 7, it is still below the x-axis. And when it gets to 7, it is above the x-axis. And it's above the x-axis from that point on. So that's what that column tells us. The plus is above the x-axis, positive side of the origin, minus is below the x-axis, negative side of the origin. Direction. Direction, if we had a sine graph, for for V of t, V of t, S prime of t, it would have a, sorry, I wanted to start right at 0. I didn't hit it just right. It would have a 0 at 11/3, and that's the only one. I didn't mention this. No. Thank goodness. Red, not blue. So sorry. And it has a 4/3 on it, and it has a 6 on it. I was looking at the zeros of the second derivative. So there would be pluses here, there would be minuses here, and there would be pluses all the way out there. If we're looking at the sine graph for V of t, that's what it would look like. So, from 0 to 4/3, it's on the positive side. No, it's headed in the positive direction. It's headed upward. From there, up to that point. At 4/3, it changes direction. And then it's headed in the negative direction. Still headed in the negative direction between 11/3 and 2 plus 2 times the square root of 3. Still headed in the negative direction between 2 plus 2 times the square root of 2, don't know where the 3 came from, and 6. And it's not until it gets to 6, to that relative minimum, that it changes direction, and then it's headed in the positive direction. So between 6 and 7, it's headed in the positive direction. It's going up. So basically, the first derivative tells us where it's increasing and where it's decreasing. So it's increasing when the first derivative is positive. It's decreasing when the first derivative is negative. Now the sine of A of t. The sine of A of t, that's the blue one, A of t, and that has the 11/3 on it. Concave down, concave up. Is that what you're seeing? Concave down between 0 and 11/3, concave up from 11/3 on. So there'll be minuses up until we get to 11/3, and there'll be pluses the rest of the way. That's where the second derivative is either negative or positive. That's where the graph is either concave down or concave up. And then finally, speeding up or slowing down. The final two columns, this one and this one, when they match. And should we think why it ought to be the case that when they match it's speeding up? Suppose the velocity is positive, and for the A of t to be positive, the velocity is increasing. If a quantity is positive and increasing, is it moving to values greater in absolute value or less in absolute value? Positive and increasing. How a quantity is positive and it's increasing, how is it at its absolute value changing? Pick a positive number, 10, and let it increase. 11, 12, 13, 14, 15, 16. Is the absolute value increasing or decreasing? Increasing. So if the velocity is positive and the acceleration is positive, then the absolute value of the velocity is increasing, so it is speeding up. That happens down here. Speeding up, and it also happens, I know I should do that in purple. We'll go with that. Speeding up. All right. What if they're both negative? Take a negative number and decrease it. Negative 10, negative 11, negative 12, negative 13, negative 14, negative 15, negative 16. What's happening to its absolute value? It's increasing. Farther away from 0. So it's speeding up. On the other hand, take a quantity that's positive and decrease it. Say the velocity is positive. It's 10, 9, 8, 7, 6, 5, 4, 3, 2. Okay? what's happening to its absolute value? It's decreasing. It's getting closer to 0. So it is slowing down. And finally, I guess those other two cases, take a quantity that's negative and increase it. Negative 10, negative 9, negative 8, negative 7, negative 6, negative 5, negative 4, negative 3. What's happening to its absolute value? It's decreasing, so it's slowing down. When the signs of those two match, it's speeding up. When the signs of those two do not match, it is slowing down. Does this feel? Yes, Danny.
Do we have to distinguish between its speeding and its speeding up?
No, I just got lazy.
So-
No, that actually doesn't mean the same thing, does it? I just got lazy. I guess in general in life that does not mean the same thing. You could be now when you're clocked on the radar, if you're going from 95 to 90, you're actually slowing. If you're in the process of going from 95 to maybe 90 to 85 to set, you're actually slowing down, but you're speeding. Yeah.
Given personal experience.
All right. So yes, thank you for having me put the up and put the down in there. Given that, is this in the top 10 easiest problems we've done this semester? Maybe. All right.
It would be if you gave us the chart.
Like on the test, we won't have all the derivatives already, will we?
That's a tough one there because it kind of that's kind of a game time decision
Yeah.
for me.
I vote yes.
I want you to believe that you have to come up with them on your own,
Okay.
but I want to reserve the right to kind of slip them to you at the last minute.
Okay.
Yeah.
Yeah, I mean, I know we could, but that's just leaving a lot more room to mess up the final answer.
Yeah.
Right. Because if you miss one of them and it's like in the wrong place, then your intervals are messed up, and yeah, it can just a small mistake. Uh-huh. Yeah, a little bitty mistake can really.
Yeah, what do you
word
word
that
problem was a tough one to factor. I don't know if I would have gotten that right.
Yeah, a word that we're going to look at in an upcoming section. The propagated error can be way larger than the actual error.
So when you screw one little thing up at the beginning and it totally messes up the entire
Absolutely.
thing.
Absolutely. All right, let's take a break. Take a break. 4.7, we're looking at some optimization problems. I think they are some of the more interesting problems. Interesting. Could mean that. But I think they are some of the more interesting problems in the course. There will be a 5-step procedure. We'll do some of these steps, maybe all the steps. Maybe all the steps in some problems. But they'll give us some guidance as to what to do next as we work our way through them. In each case, what we're going to look for is a quantity to be optimized. It might be we want to find the maximum area, subject to a certain the idea of find the maximum area if we know the perimeter of a given rectangle. What should the dimensions be? Trying to maximize the area. This first example that we'll look at, it's going to be determine the dimensions of a rectangular solid with a square base and no top. If we want to maximize the volume, so there'll be some quantity. We want to make the volume as much as possible, but there's a constraint. If we had a limitless amount of material and consequently a limitless amount of surface area, then we could make the volume just as much as we want. But if it's a certain amount of surface area, there could be different shapes, different combinations of dimensions, all with the same surface area, but some with more volume than others. So what we'd want to do is make the volume as much as possible in a case like that. Maximize the volume. So, so step 1, we would draw a picture. Step 2, figure out what the quantity is that's to be maximized or minimized, and express that quantity as a function of usually a couple of variables. In the problems that we'll look at, there'll be a couple of variables. And then we'll call that the primary equation. Volume equals blah, or area equals blah, whatever that is. That's that's a function. We'd like to be able to take the derivative of that. We'd like to be able to set it equal to 0. We'd like to be able to look for critical numbers and find relative extrema with a view toward finding an absolute maximum on a particular interval. But we may have more than one variable. And so if and there generally are, a couple of variables, we want to find an equation which relates those variables with each other. This is usually called the secondary equation there. And we'll take that equation and solve it for one of the variables in terms of the other variable. Take that expression that we get, substitute it for that variable in the primary equation, and get it down to one variable. So we have the quantity to be optimized as a function of one variable. Then we could apply some calculus to it, one variable calculus. Take the derivative. We will look for critical numbers, and then we will use these techniques of the previous section. Now, step 4, if I'm lazy, I may skip over step 4, but really I shouldn't, because in real life there might be certain physical restrictions on the particular problem. We wouldn't want to be values where if it's, like I said, it's area, we wouldn't want any of the dimensions to be negative. We wouldn't want the area to be negative. There could be certain situations where they just won't work, and this may help us actually finding if it's like negative infinity to positive infinity. If we put certain restrictions on it, we could find ourselves dealing with a nice closed interval, and we could apply the extreme value theorem to that. So it can actually help us to do step 4. So I'll try to be careful to do that. So we'll work through as many of these steps as possible in each problem, beginning with example 1. I wonder if I've already pasted it there. Nope. Let's paste it here. Determine the dimensions of a rectangular solid with a square base and no top. If its volume is to be maximized, its surface area is to be 500 square inches. So square base and no top. Let me see if I can draw a rectangular solid. Something like, come on. This, and this, and this, and this. Oh, seems too steep. I like that, and that, and that, and that. So this looks like a cube. I don't want it to be a cube. Okay, it doesn't look like a cube to you. Good. So here's our rectangular solid, and it has a square base. So to indicate the fact that it's a square base, I'm going to call this x and this x. Those consecutive side lengths of that rectangular base should be the same. So it's x all the way around on the bottom, and on the top, of course, as well. The other dimension is y. It might not be a perfect cube. If it's a perfect cube, the problem's done, because it's up to us to figure out what are the dimensions of this, the relative dimensions that are going to result in maximizing the volume. So it's x by some other dimension y. Now, this is the picture. This is step 1. And what we want to do is come up with our primary equation. We want to express the volume as a function of these variables that we see. Well, what's the formula for the volume of a rectangular box?
X squared plus y, I guess.
Well, in this case, if we're going length times width times height, it's going to be x times y. So yeah, v equals x squared times y. Area of the base times the height. That's our primary equation. Now the secondary equation involves the constraint. So step 1, the picture. Step 2, the primary equation. Step 3, the secondary equation. The constraint, the surface area. Now notice that it is a box with no top. Now as far as the surface area, I'm going to count the surface area of the outside, the bottom, the 4 sides. Now, if it has no top, yeah, that means we could reach inside, and that's actually a surface. But I'm not going to consider that in the calculation as far as it's telling me 500 square inches. If we wanted to consider that, maybe we do the same problem except double it. But just perhaps the problem should have been clearer as what counts as surface area and what doesn't. But for my purposes, my understanding, I wrote the problem. Maybe I should have written it a little bit better, but my understanding of this is it's going to be just the outside of the box and the bottom of the box. We need the sum of the areas of the bottom and the front and the back and the left and the right sides. That's our secondary equation. We're going to set it equal to 500. So surface area equals 500. So I'm going to say x squared plus, well, the right-hand side is xy and the left-hand side is xy. The back is xy. The front is xy. So I want to say that's 4xy. Does that sound good? Left, right, front, back. X times y. Each of those rectangles is x times y because that's y, and that's y, and that's y, and that's x, and that's x. So x times y. So x squared is the area of the bottom plus 4xy equals 500. That's the secondary equation. This equation gives us a relationship between the variables x and y, and we need that if we're going to eliminate one of the variables from the primary equation. Now, if we had an x squared in the secondary equation and no other x's, I would say maybe solve it for x squared and take that expression and substitute it for x squared in the primary equation. But we've got an x squared, we also have that xy term, so I'm thinking maybe solve the secondary equation for y. Y equals some expression with x's in it, and take that expression and substitute it for y in the primary equation. I think that's going to be the way to go. So still on step 3. 4xy equals negative x squared plus 500, or 500 minus x squared if you prefer. If we divide both sides by 4x, y equals negative x squared plus 500 all over 4x. And maybe I'll leave it like that for the moment. Yeah, let's leave it just like that. Take that expression and substitute that expression for y in the primary equation. So still step 3. V equals x squared times negative x squared plus 500 over 4x. So it looks like the x divides out one of those factors of x in the x squared. And the 4 in the denominator can come out in front as a 1/4 if we want it to. So I'm going to say this is 1/4 x times negative x squared plus 500. This x down in the denominator divided out one of those x's, and so that x squared just turned into an x, and the 4 came out in front as a 1/4. And since we know we're going to have to take the derivative of this in step 5, it'd probably be good to go ahead and expand it so we have, we don't have to use the product rule, we can just use the power rule. So V equals negative 1/4 x cubed plus 4th of 500. Maybe that's 125 x. So this is the volume function. If someone gives us this dimension, the length, either one of these bases, and then says, okay, subject to these constraints, 500 square inches of surface area, you can calculate the volume by substituting that one dimension in per x, and it will tell the volume that resulting rectangular box will contain. Now, any restrictions, 4 has to do with any restrictions on the values of x that could be potentially helpful. And we could look back at the diagram, not necessarily just at this. Oh, it might help us to look at this. certainly, so if I'm looking at step 4 here, certainly x would need to be greater than, well, I don't even know if I want it to equal 0. It's going to be greater than 0. If x is too great, though, what if we used all 500 square inches on just the base, and we didn't have anything left for the sides? What would x be if x squared was equal to 500? Well, I guess the square root of 500, whatever that would be. The square root of 500, it would be
22.3.
22.3? All right, so let's say x has to be less than the square root of 500, which is about 22.3. Now, I don't think the function is going to be badly behaved. Will it be bad? It's a polynomial. It's not going to be badly behaved at 0 or badly behaved at the square root of 500. So what we could do is this. If we know it's not going to be the endpoints, the maximum or minimum, we could find the absolute maximum of v, or I can say v, well, I'll just say v, on the closed interval from 0 to the square root of 500. If it happens to one of the endpoints, I can't see it happening on the endpoints. It's going to be 0 at both endpoints. So I don't think it's going to happen there. But if we do that, then that will be the absolute maximum volume that we're looking for, and it'll tell us the value of x where it happens. So I like the closed interval because we can use that process of finding extreme values on a closed interval, and the extreme value theorem will work. So finally, step 5. Take the derivative at v prime of x equals negative 1, what's 3 times negative 1/4? Negative 3/4 x squared plus 125. And I'd like to set that equal to 0 to find first order critical numbers. So negative 3/4 x squared plus 125 equals 0. Well, an extra step, I guess. Negative 3/4 x squared equals negative 125. X squared equals negative 4/3 times negative 125, which is, I don't know what that is. It's not nice.
That's 166 and 2/3.
166 and 2/3. I guess I could write it 500 thirds, but that's what it is, 166 and 2/3. X has to be positive. X can't be negative, so x is going to be the positive square root of this. So x in general would be plus or minus the square root of 500 thirds, but of course we can't use the negative one. So the only meaningful critical number is the square root of 500 thirds, and I believe that's the value of x that we want.
12.9.
So x is about, we'll call it 12.9. I'd like to believe that this is not the location of a relative minimum. But I think all I have to do is plug it in and see, calculate the volume. So what is v of 12.9, or v of the square root of 500 thirds? Negative 1/4 times 12.9 cubed plus 125 times 12.9 is about what? What's the volume?
12.9.
Yeah, if we evaluate it at 12.9,
I got
how many cubic inches?
I got 0.1925.
Ooh, I'm worried.
Well, I didn't add in the 12.9 at the end.
Let's
Or the
see.
X at the end.
Negative 0.25 times 12.9 to the power of 3 plus 125 times 12.9. 1,075? 1,076? A little concerned with significant figures here, the way I'm rounding, so I'm going to say 1,076. It says find the dimensions. I have the base. I don't have the height, though. How could we find the value of y, the height?
Plug it into the line first.
That'd be one way to do it. Plug it in right there. So we could say negative 12.9 squared plus 500 divided by the quantity 4 times 12.9. 6.46 or about 6.5. So y is about 6.5 inches. And I believe if we were careful with the radicals and we just work with the radicals instead of decimal approximations, I believe it can be shown that x is exactly the square root of 500 thirds and y is exactly 1/2 of that. 1/2 of the square root of 500 thirds. And in general, when this problem is done with a rectangular box, a fixed surface area, and no top, in order to maximize the volume, the height has to be exactly half of the length of the base. And if we began and just said, let the surface area be S instead of some specific number, we could express it all in terms of that and show that y was exactly half of x. But we've got specific values here. So these are the dimensions. And this is the volume. There are a couple ways I know that's a maximum and not a minimum. A relative maximum instead of a relative minimum. I could apply the first derivative test and evaluate the first derivative a little bit less than 12.9, a little bit greater than 12.9. Or I could take one more derivative and apply the second derivative test. V double prime of x equals negative 3/2 x. But since the values of x throughout the interval are positive, V double prime is negative throughout the interval, meaning concave which way?
Down.
Concave down. So it's going to be a maximum. Relative maximum. It's the only relative maximum in that interval, so it's an absolute maximum value. All right.
The minimum